Hello, everybody. Welcome back to yet another ZNotes live session on physics. And today, as always, we've got Kaleem here with us. And today, we're going to dive into atomic physics. We're going to look at the Goldfile experiment and what Rutherford concluded from it and what it means for our understanding of atoms. So, without further ado, Kaleem, please take it away.
Thank you very much, Pugs, guys. I am aware that GCSE exams are starting this week on Friday. And, you know, a topic that comes up quite a lot is atomic physics. And what I really hope that you get amazing value from this before your exam, in that we try to kind of weigh this up. Yes, it's always good to go over exam questions, but this week, if we can get there, brilliant. If not, the goal is there's like 4 areas in the atomic physics topic that are fairly popular in exams. 3 of them we are going to try to go over in the next 2 lessons. One of them is Rutherford scattering experiment. The other one is radioactivity and half-life, 2 separate things. And then the last one's applications, which is going to be the one of the 4 that I do not go over, because for me, that is simply a student knowing what they've learned and figuring out that, very briefly, that radioactivity can be used for medicinal purposes like tracers inside your body, so they can detect blood clots, that it can be used for killing cancer. Yes, it can cause cancer, but atomic physics, radioactivity can be put to good uses as well. It's always given a very bad name, yet there are advantages. The issue is when things go wrong, they tend to go horribly wrong, and I think that's the big thing with radioactivity. Otherwise, it's very, very useful. So today, as Pug says, we are going to look at Rutherford scattering experiment, which was actually conducted by students and gave us, mankind, if you like, the idea of what the atom looks like. Now, what is popular belief of an atom? That an atom has a very dense nucleus that is made up of protons and neutrons, protons being positively charged, neutrons having no charge. And round the outside, we've got negatively charged electrons. And normally, in a neutral atom, the number of protons and the number of electrons are equal. Okay, it's said to be a neutral. Same number of pluses, same number of minuses. Now, what you're going to learn later is that radiation causes ionization. In chemistry, ionization is loss or gain of electrons. Here, you're going to find with atomic physics, it means nothing but loss. This is likely for Thursday's lesson, but today, let us go into Rutherford scattering experiment. So, I've already said proton, positive charge, atomic mass 1. Neutron, no charge, neutral, 1 atomic mass as well. And electrons, a very, very small atomic mass, very often considered to be 0, with a charge of -1. So one of the nice bits about atomic physics and radioactivity is if you do chemistry, there are gifts for you in the exam, or there could potentially be gifts for you in the exam. Now, nobody's asking you to memorize a periodic table, but you are asked to be familiar with nuclide notation. In other words, you should be able to look at this and go, okay, that's helium. If not, they'll give you enough of a clue. You should know that the top number is known as the nucleon number. In my day, it was called the mass number. The nucleon number, which is the number of protons plus the number of neutrons in the nucleus. And down the bottom, the proton number, again in my day, called the atomic number, which is the number of protons. So this helium, all right, has 2 protons, because I can tell because of the bottom number. It has 2 electrons, because in a neutral atom, the number of protons and electrons are the same. And maybe a little bit confusing, there could have been a better choice here. It also has 2 neutrons, because the nucleon number is protons and neutrons. So it's 4 minus 2, which is 2. So the neutron number, well, the number of neutrons is the nucleon number minus the proton number. An isotope is an atom with the same number of protons, but a different number of neutrons. So we're kind of defining some stuff that hopefully you've learned in chemistry. So here we have 3 isotopes of oxygen. Notice their proton number, also known as the atomic number, is exactly the same. But notice their nucleon number, also known as the mass number, is different. Now, what does that mean? Well, if you look very carefully, Each of these has 8 protons, and in a neutral atom, it will also have 8 electrons. But the number of neutrons is 16 minus 8 for the first one, which gives us 8, 17 minus 8 for the second one, which is going to give us 9, and 18 minus 8 for the last one, which is going to give us 10. Now, what's the big deal here? Okay, so 8 neutrons, 9 neutrons, 10. Because they all have the same number of electrons, isotopes have identical chemical properties. But because they have different number of neutrons, isotopes have different densities. Some isotopes are unstable and they're said to be radioactive. Now, this is where I want to take some time with you guys, because lots of students have got no idea why things are radioactive. Now, I'm generalizing right now, but if you do chemistry and you've looked at the periodic table, kind of towards kind of the bottom and slightly off to the right, there are these two rows of metals that generally you never talk about in chemistry. If you looked in there, you'd probably find strontium, plutonium, uranium, mercurium. Don't even know if I pronounced that right, but there's all these ems. And these elements are said to be unstable. What does that actually mean? Well, basically, you're going to learn more on Thursday. It means they give off either alpha, beta, or gamma, or more than one. So, alpha radiation, which you're going to learn about, is a helium nucleus, beta, which is a fast moving electron, and gamma, which is a high energy electromagnetic radiation. In other words, light that we cannot see, very high frequency. So, what happens with these elements? Well, over a period of time, and we give it a special name, this period of time known as the half life. But before we get there, over a period of time, these elements will give out alpha, beta, gamma. Let's just keep it simple. Let's just say something gave out alpha only. Well, it will decay, give out alpha, and at the same time, that radioactive atom will change into another atom. For the sake of simplicity, let's just pretend that atom was stable. Let me give you a kind of slightly different example. Carbon 14 is radioactive and there are small amounts in our body. Carbon 12 is non-radioactive, and that's primarily, we've got a lot of carbon 12 within us. Carbon 14 is an isotope of carbon 12. When carbon 14 decays, eventually it will turn into carbon 12. What do I mean by decay? It's giving off radiation, okay? Whether it's alpha, whether it's beta, whether it's gamma, whether it's a combination, it's giving off radiation, and over a period of time, it changes into carbon 12. Now, it actually happens, so carbon 14 has a humongous half-life, huge, like 5,700 something years, rounded. Now, you might go, how the hell do they know that? Has someone been living that long? No. Using clever mathematical principles and technology, they can figure out that it's 5,700 years old. I don't know if you guys have been fortunate enough to grow up with the stories of the mummies in Egypt, the pyramids, Tutankhamun. I used to be very fascinated by this as a kid. And what used to fascinate me even more when somebody said, yes, this mummy is, I'm just going to make this up now, 20,000 years old. And you're like, how the hell do you know that? And one of the methods that they used was radioactive carbon dating. Now, I know I said I wouldn't go into an application, but I'm trying to give you a feel, rather than just going, hey, we've got alpha, beta, gamma, we've got isotopes, we've got all of these elements, and here's all the numbers and blah, blah, blah. I want to give you a kind of feel for what's going on here. All right. And just as a side note, you'll hear of politics between countries where they'll accuse other countries of enriching things like uranium or plutonium. In other words, making it more radioactive, making it more potent, if you like. So I hope this gives you kind of a basis of where we're headed. But the first thing is all about deep diving into Rutherford's scattering experiment. Now, what was this all about? It was carried out by students, and basically, what the experiment was about was firing alpha particles at thin gold foil. Now, what are alpha particles? You're going to learn on Thursday a helium nucleus. Now, please, When I say helium nucleus, I do not mean that stuff that you go to a birthday party and there's a balloon going up to the ceiling and you grab a hold of that balloon and you stick a little hole in the balloon and you breathe in that gas and you talk funny. It's not that stuff. All right. In fact, if you did this with alpha particles, there's a very good chance that you will be seriously, seriously ill, if not gone. All right. You're going to learn on Thursday that alpha is the most ionizing radiation. But here, alpha particles are a helium nucleus. And you might go, but sir, what's the big deal? What's different? A helium nucleus has no electrons. No nucleus has electrons. An atom has electrons around it. And some students think, does it really make it all that different? Yeah, it does. It absolutely makes it different enough to make it very dangerous for us in some ways and safer in others. You'll learn all about that on Thursday. So anyway, we fire these alpha particles at this thin gold foil. Now, guys, I would maybe Pugs bring you into this. Pugs, if we had a fishing net, right? And let's just say the squares, it's going to look more rectangular, but let's just say the squares in the fishing net, they're probably not even squares, but I think you get the idea. The gaps in the fishing net, let's just say each gap was the size of me. Now, to put that in perspective, I know we've never met in person, but I'm 6'2", and I'm told I've got broad shoulders, but I'm 6'2", and if we had nets with gaps like that, Pugs, do you think we'd catch a lot of goldfish?
Heck
Why
no.
not, Pugs? You got to get. I think you've just muted yourself, Pugs, accidentally.
Oops. That's because the goldfish is so tiny compared to the size of the gaps in the net. So the goldfish should just go right through the net. That's all.
And I don't know if I only heard about this recently. My 9-year-old son, I don't know where he heard the word Megdalon. I'm like, what the hell is a Megdalon? And I watched a shark film recently where it's this prehistoric shark that was apparently the biggest shark ever. You should look it up. Now, not only, well, actually, maybe this is a bad example because Megdalon would probably chew up the net like there's no tomorrow. Apparently, Megdalon would probably chew up a jumbo jet. So, bad example. Do you think, Pugs, maybe this net could catch perhaps a dolphin, perhaps a whale, perhaps maybe a shark? Let's just pretend the netting's quite strong, right? Megdalon, like when I saw this Megdalon character, he would eat it. No, he would eat it, no problem at all. But I'm wondering about normal mammals and sharks, and etc.
Should be able to do that, yeah. Because they're kind of large, like a whale is huge.
Exactly.
It's
so
huge.
Thank you, Pugs. And I hope viewers at home are seeing the same thing. Now, you might be wondering, where am I going with this? Guys, I'm wearing a t-shirt right now and a shirt, and they look fairly solid, right? And if I took a t-shirt out here and I, let's say, poured sand over the top, I hope you agree, very little, if any, of the sand would go through the t-shirt. Yet if I took a glass of water and poured it over the t-shirt, I wouldn't do that here because I got a microphone, but the water would seep through. Why is that? Well, basically the water molecules are small enough to get through the gaps in the t-shirt. Where am I going with this? To you and I, aluminium looks solid. Imagine kicking a football off a wall and the ball didn't come back. I mean, you'd be like this to the wall. Like, what the hell's going on with you? Right? So, what you're going to find here is, to you and I, gold foil is as solid as they come. I mean, I could pour water over gold foil and it would just go off to the side. It wouldn't even go through the gold foil. But what you're going to find with Rutherford's experiment was that, think about this, alpha particles, helium nucleus, right? So now in kind of particle terms of an atom, we know what actually happens to be the biggest part. Yeah? Let me give you one last example. Imagine you're Thanos, right? And you're big enough to carry the planet Jupiter. I know I've got all these kind of fantasies in my head, right? So you're Thanos, you can carry Jupiter. I'm Iron Man, right? I'm kind of hovering in space, and Thanos tries to throw Jupiter at me, right? Because he's really strong. Forget Thanos for a second, guys. I want you to think about Jupiter in the solar system. How likely, right, is Jupiter to hit another planet in the solar system if Thanos just randomly throws Jupiter in the solar system? How likely? What do you think, Pugs?
Not so much because I mean Jupiter's big. That's kind of true, but solar system's mostly full of empty space. So I don't think that's
So the
likely.
solar system is absolutely huge in comparison to the
Yes,
planet, right? So basically, this is the whole point. Even
the
though it's a
largest
huge
planet.
planet, there is no way, or well, not no way, but it's very, very unlikely to hit anything in the solar system. So this is the whole point. So what I want you to understand, kids, is that you've got this gold foil. To me, you and everybody else, it looks absolutely solid. Yet when you fire alpha particles at it, the overwhelming majority of them go straight through. I mean, like 95, 96, 97 plus percent of alpha particles go straight through. Very, very few deflect off to the side. Now, what the hell happened there? Why did some of them deflect off to the side? I hope viewers at home know what the crossbar challenge is. I don't know if you've ever played it as a kid. All right, when you're bored on a football pitch, somebody challenges to take the football and hit the crossbar. Now, back then, I'd be lucky to hit it 1 in 10, right? Now I'm actually a bit better, but back then it'd be about 1 in 10. Now, what's going on there? The ball goes either over the bar, under the bar, past the post. You're really bad if you put it past the post. Really, it should be over the bar or under the bar. But the thing is, when it hits the crossbar, it's hit something solid. There's all this empty space round about. And this is the whole point. What Rutherford discovered, I was going to say students, but what Rutherford effectively discovered was that the atom is mostly empty space. This is going to sound really rude. It means you and I are mostly empty space because we're made up of atoms. And it kind of sounds really hollow, right? So very, very few alpha particles bounced off to the side, and even fewer bounced back. I mean, like, 1% or less. So what does this experiment tell us? I mean, just like my experiment with a fishing net and all the goldfish go through, it basically says, hey, you're not fishing very well. Get a net with smaller gaps. What this experiment told us is that the atom is largely empty space. Here's another way of doing it, a zinc sulfide screen. This is actually the method I use in my book. I don't know if you remember as a kid, Pugs, having these magic pens. So you'd write in white ink and you'd either use a UV light or you'd use other
Yes.
color to bring up, right? So what happens is, just to help you understand this, a zinc sulfide screen makes something appear. And the way it does it
Okay.
scientifically is it fluoresces. So what
Mhm.
happens is the alpha particles hit the screen and the screen gives off a color. And what happens in this experiment is the overwhelming majority of them go straight through, and very few of them bounce off to the side, and even fewer bounce straight back. You got that?
Yes.
Brilliant. So let's now look at this in a kind of macroscopic scale. Imagine these kind of red circles, if you like, is my gold nucleus, and that big circle is the gold atom. And imagine these things coming in from my left are the alpha particles. Look what's happening. They're going straight through the middle there because the atom is mostly empty space. All right. So this was Rutherford's overwhelming conclusion. Like 98 plus percent of them went straight through. Then, okay, so this is his conclusion. Then you get some of them that get very close. Now, notice it didn't hit. It gets very, very close and bounces off to the side. Now, why did it do that? And why doesn't it hit? Well, on Thursday, I'll explain this in a lot more detail. But basically, the nucleus is positively charged and the alpha particles are positively charged. And what's happening is they come very close and they deflect. But notice they don't hit because positive and positive, what does it do, Pugs?
They repel.
They repel. Absolutely. So, you've got maybe a percent less than that are deflecting off to the side, and even fewer. Okay, now this is overwhelming. Now, watch this. It doesn't hit at all. Bounce straight back. Okay. Now, What did then Rutherford conclude? Now, remember, his students did this, but when it comes to the exam, it's Rutherford that takes the credit. What did he conclude? He basically said the atom is overwhelmingly mostly empty space, that there's a very, very dense nucleus in the center, and that it was positively charged. Why? Again, let's have a look at this. Here's a typical atom. You've got these orange kind of dots going around the outside. That's your electrons. Positively charged nucleus in the middle. And that kind of orange halo, if you like, is the entire atom. So if the alpha particle is miles away, what does it do? It goes straight past. The closer it gets, watch what happens. Deflects a little, gets closer, deflects a hell of a lot more, and goes straight at it and bounces straight back. But look what happened. It did not hit. So, again, to wrap this up for today, Rutherford said the nucleus is very, very small and dense. Why? Very few alpha particles hit it. Positive, because when it came close, it repelled. Dense or heavy. Why? It's the alpha particle that moved away, not the gold foil. It's a bit like a football hitting the crossbar. It's not the goal that moves very far, it's the ball that's going to move. So here is your last diagram. Look at the diagram carefully. If the alpha particles are very far away from the nucleus, look, they go straight through. If they're close, they bounce off to the side. If it's above, it'll go above. If it's below, it goes below. And if it's straight at it, it tends to go straight back. Now, look, guys, in the exam, they tend to make it go off to the side slightly. Why? Because very often it's hard to draw it going straight back. So to make it clear, they make it go off to the side. Now, so very often I like to kind of slag off my chemistry colleagues and say physics was the daddy. We told the chemists what the atom looks like. I'm sure they'll contest that. So this is what people believe the atom looks like in this animation here. And in actual fact, that's just a 2D drawing. This is what it looks like in 3 dimensions. But look, you don't need to worry about that for your exam. Stick to the 2-dimensional drawing. It's just 3 dimensions is much cooler. Pugs, I mean, I think that's me done, wrapped up. If your audience have got any questions, I'm all ears. Otherwise, I will see them on Thursday.
Well, we don't have any questions right now, but you can drop them in the comments below, and we'll get back to them soonest. Thank you, Kaleem, for this amazing session. Let's wrap it up for today, and let's do radioactivity on Thursday, and we'll explore this a lot more in depth. Thank you. See you.
Thank you very much, Pugs. Thank you, ZNotes.